Hello, everyone. We are back again. My name is Per, and I'm going to be the host for the rest of this already amazing day. Almost feels like a game show thing, right? I'm going to be your host. So for this session, I'm very happy to introduce Jérome, who has recently joined the M&I as a postdoctoral researcher, and he has been actively contributing to Nilearn for a couple of years now, one of the driving forces, I would say. And he will now talk about automatic testing that is continuous integration. And Jérome, I'm just gonna focus your slides and then take it from here.
Okay, thank you very much for the introduction, Pierre, and thank you for having me. And as you said, I will be talking about continuous integration and automated testing and how this is implemented in Nilearn. So continuous integration is a software development practice where there is one central master branch that is common to all developers, and developers keep merging in regularly small changes, iterative changes into this master branch. And what is essential is that the master branch is always kept clean and bug-free. So this practice relies heavily, obviously, on version control and also on automated testing and quality control. And the motivation is that software should be like firefighters who are always training and drilling and performing exercises so that when they need to, they are always ready to go to work. And once on site, they can face any situation and they are well prepared. And for a software, this means that the master branch should be kept always updated and integrate most of the recent work of the developers. And most importantly, we want to be constantly testing it, running through a very complete test suite in diverse environments to make sure that nothing is breaking and that it is ready to be deployed in production or to be released. And some projects go even further than that and actually do continuous deployment where once the test suite has run, someone just needs to approve the deployment for the branch to go in production, or even continuous delivery where no manual intervention happens. And once the test suite runs, the code goes directly in production. So in this talk, I'll be focusing on this automated testing, which is to really ensure the quality of our master branch by keeping testing it constantly. And before merging any patch from one of the developers, running the candidate merge commit through the whole test suite to make sure that we are not breaking anything with this change. So this is a natural follow-up to Chris's talk because he explained to us how to write a good test suite and test our software. And now we will see how to run these tests automatically with every commit. And the good news is that now we can actually set up this automated testing very easily and for free with online platforms. So just to make things concrete, I created a toy package that doesn't really do anything useful, but that's here on GitHub, and I will show how to set up automated testing for this package. So it's just a placeholder. It has basically just one function that takes a bunch of coordinates in M&I space and returns a map which contains Gaussian blobs at these coordinates. And we will be adding a continuous integration for this project. So the layout is very similar, is the same as that of Nilearn or scikit-learn. Starting from the root of the repository, which is the directory which contains the setup file. We have the package itself, which is the directory with an init file. And each subpackage contains a subpackage that contains all the tests for the corresponding modules. And this is a very classical and sound layout. There is just one drawback, is that if we run the tests from the root of this directory, the package itself is in our Python path. So we have to be careful to make sure that we are testing the code that is installed and not the package that happens to be in the directory. Because otherwise, as Chris mentioned, this can lead to some surprises. Of course, when doing this locally, but I'll come back to that later. So just to stress that point, a small example, in this version, I introduced several bugs in the code. So here is a function that loads some file with examples coordinate that is packaged with the code and returns it. But we see in the setup that I forgot to add it to the package data. So if I use this function from the root of my repository, it will work because this file just happens to be there. But it won't be copied to the distutils when the package is installed. So on a user's machine, it will not work. And I am also here using this operator, which is new in Python 3.8. So it will run fine on my environment, but on most users' environment, it will result in a syntax error. And despite those mistakes, as I said, if I run naively from the root of the directory, the pytest command, seemingly everything is fine, the tests pass, and all the code is covered. So to alleviate this problem when testing locally, we could be using Tox, which will automatically take care for us of setting up a bunch of virtual environments and possibly changing to a different directory to run the tests so that we can test our package against many different Python versions and dependency versions. But still, it's even better to test on an environment that's completely independent from the developing environment. And moreover, we probably want to be testing on several platforms, Linux, macOS, and Windows. So we want to run all of this on separate virtual machines. And also, most importantly, as I said, we want to be running this whole test suite on many environments in a systematic way so that no change that would break any of the code gets merged into master, and that if some problem creeps into master, it is caught right away and fixed very quickly. So we want to be constantly and completely automatically running our whole range of tests. And this is where continuous integration platforms come in. So we, for example, there are many of them. Nilearn uses Azure pipelines, Travis, and Circle CI. And to set them up, it's always the same process. We create an account, point it to our GitHub repository, and tell it to follow the repository, and add a configuration file for this platform that we check in to the Git repository. And then when we push to certain branches or when we open a pull request on the GitHub repository, GitHub will send a notification, for example, to Azure pipelines, and this will trigger a build. So when Azure receives this notification, it will start a virtual machine on the Microsoft server in which it will clone our repository and then read the configuration file and execute whatever we are asking for in the configuration file. So this will generally be, of course, some our unit tests, and also, for example, in the case of Nilearn, building the documentation, running all the examples to get the plots that go in the example gallery, and some linting of the code to make sure that everything works out. And we also have the possibility to store some outputs of this build that we call artifacts. So for example, we can store on the infrastructure the documentation that we have built so that we can later on download it and look at it and at the examples and make sure that everything is looking good. One detail that I think is worth pointing out is that when the build has been triggered by a push on a branch that has an open pull request, GitHub creates a merge commit between the pull request branch and master, and this is the ref that is checked out by Azure Pipelines and or any other CI tool, and that is used to run the build. So that's also why it's important for PR branches to always keep close to master, and if a branch stays away from master for a long time, it's worth regularly merging master into this branch so that it doesn't get very different. And of course, if there are conflicts between master and our branch, the CI will not run at all. So really, in keeping with the idea of continuous integration, we want our development branches to be always up to date with master and easy to merge. Now I will very quickly walk through how to set up this continuous integration for Azure Pipelines. And I hope to convince you that it's really easy and worth doing. So as I said, the main steps are that we add a configuration file in our repository that will be read by Azure Pipelines and tell it what to do. We create an account on Azure Pipelines, and that's it. After this, whenever we push a new commit or open a pull request, it will run our build and our tests. And then in a second time, we will add the fact that we want to save some artifacts and upload code coverage reports so that we can see them in the pull request pages. So we will add a configuration file that has to be called azurepipelines.yml, and it is in the root of the repository. It has to be there so that Azure finds it. And in our case, we will also include in it a template that we could put wherever we want in the repository, as we will see later. Now we can have a look at this file. So as you can see, it's very short. First, we tell Azure what should trigger a build. So in this case, we want it to run the tests whenever we push to the master branch, and implicitly also it will do it whenever we push to a branch that has an open pull request. And then we have a section called jobs. Yeah, by the way, this is in YAML format. That's a superset of JSON. And here we just have a list of jobs, which is a list of everything that it should do when a build is running. And in this first example, there is just one single job. So it's this one. We tell it which virtual machine to use. Here we're running the tests on an Ubuntu machine. We can define some environment variables. Can you see my mouse? I hope so. Yeah. And here we have a matrix of parameters of the environment on which we want the test to. Okay. Well, okay, so I'll just read out loud. Under this matrix session, so we define the parameters, and this defines a matrix in which so the tests will be run in these two environments. So here, as a trivial example, we just run them with two different Python versions and two different versions of NumPy. And then below this, we have the steps, which are the list of all the steps that will take place when we run this job. And I could just include it here in the same file, but it wouldn't fit on the slide. And also, we might want to reuse this list of steps for different jobs. So I put it in a separate file that gets included here by using template. And it's a template, so it could be expanded to different values. But here, I'm not using any parameters at all. So this other file just gets included verbatim as it appears here. and it's just the list of steps that will run when this job is executed. So the first is a task, so it's a step that's already pre-configured and made available to us by Azure Pipelines, and it tells it to use the Python version that we have specified. Then we have a script to install our dependencies with pip. And in the third step, we have a script that actually runs the test suite, as Chris has explained, using PyTest. And we just make sure that we don't execute this from the source, from the root of the repository, which actually contains the source package, so that we are testing the version of our package that is installed in these utils. And finally, we want to publish the results of the tests. So again, here we have a task that's already pre-configured, and we tell it where PyTest has stored its output. And we also specify the condition, because by default, a step will only run if the previous steps have succeeded. But here we want the results to be published even if the tests have failed, or especially if the tests have failed. So we specify the condition that it should go whether the previous steps have succeeded or failed. And that's it for the configuration. Now we just have to create an account and point it to our repository, which is the most annoying part, because it involves clicking on a bunch of buttons on the web interface. But it's also quite quick. So here we go to the Microsoft DevOps website. We can sign in with GitHub. And so we can just reuse our GitHub account, create a user here, and then we have the possibility to create a new project. We give it a name, decide if it should be public or private. And we will land on this page where the interesting part for us is this pipelines tab. So we will click there and have the possibility to click here to create a pipeline. Then it will ask us where it can find our repository. In our case, it's in GitHub. And it will show us the list of our GitHub repositories, and we can pick from that. And then here we can see the YAML configuration file that we have just added to the repository, and which will configure the build. And now we can just click on run, and it will already start running our build and executing our tests on the Microsoft Azure infrastructure. So here at the bottom, we see the two jobs that we have configured that have begun running. And if we click on them, we can see all of the steps executing. And as we're running this on a fresh environment, if we introduce the mistakes that I showed earlier, some of these tests will fail, and we will be notified early that we are at risk of introducing bugs in our master branch. Now we can also get this information from GitHub. So many projects add a link to their README page that looks like this, and which introduces the icon we see on the left here, that is green if the Azure Pipelines build has succeeded and red otherwise. And in the pages of pull request, at the bottom of the page, I'm sure most of you have seen this before, we see a list of all the continuous integration jobs and their status. And from that, it's really easy to make the build more comprehensive. So, for example, we can also test on Windows by just adding a different job. It's pretty much the same, except that here we change the virtual machine that we want to use to run our tests on Windows, and we include exactly the same steps. And now we will also be testing our library on Windows. Now, I mentioned that an important step is to store artifacts. For example, Nilearn will store the HTML documentation that it builds. Actually, it doesn't do that on Azure Pipelines, but on Circle CI, but that doesn't change anything. So in this toy example, the artifacts that we want to store are just one plot, because we will run an example that saves a plot made with Nilearn. and we will store it so that we can later download it from the online interface and check that everything has worked well and that the plot produced by the example is looking good. So again, a very simple job. The first step is the same. We specify a Python version, then install our dependencies with pip, then we run our script, and finally there is this publish step where we just have to specify where is the file we want to save on the virtual machine. It could also be a whole directory, and the name of the artifact, and it will store it online. And then if we come back to the interface that I showed earlier that shows the build, we can just click here and download the artifact that has been stored. Then the next step is to add a coverage report. So in the previous session, we talked about code coverage, and we want to make sure that as much as possible of the code that we introduced is correctly covered by unit tests. So of course, the fact that it's actually the code gets run and is covered is not a guarantee that the tests are actually any good, but for sure, if the code is not covered by the tests, we need to improve our testing. And there's this platform called codecov, which is very practical because all of our jobs that run in different machines and possibly even on different continuous integration providers will just upload all of their reports to this platform, and codecov will aggregate all of them and produce a unified report that tells us if a line has been executed on any of those jobs in any of these continuous integration platforms. So we just need to get from continuous to send into codecov. Again, we can do this with our GitHub account. And when we visit the URL that you see here, that points to our user and the name of our repository, our GitHub username and the name of the repository, it will show us a token, which is like a password, that we use to be able to upload coverage reports for this directory. If you're using a public repository on Travis or CircleCI, you don't need this token, but you will need it at least for private projects. So once you have copied it, you add it to the variables in Azure Pipeline. By editing the pipeline, you go into variables and add the token, and you make it a secret. And then there's just one detail. We need to go into triggers, and here tell Azure to make this secret variable available to builds that are triggered by pull requests by forks of our repositories. Otherwise, they won't be able to upload codecov. And in our case, it's fine to make these secrets available because they only contain this single token for codecov. And this is what Nilearn and scikit-learn do. And once we have done this, we just need to edit our job to add a step that tells it to upload the reports to codecov. So it's the last one we see here. And it's also very convenient to do because codecov makes available to us a bash script that will upload the report. So we just need to download it with curl and execute it and giving it the token, and everything is taken care of. One thing we must do is that by default, Azure will not make the secret variables available as environment variables. So here in the env environment section, we have to explicitly tell it to map our secret variable to an environment variable. Once we have done this, we can also optionally add a codecov YAML file configuration to change the behavior of codecov. So for example, here we change the threshold that causes a failure to tell it that if the pull request decreases the code coverage by 1%, that's acceptable, just to avoid failures, noisy failures due to small fluctuations. But if we don't include this file, it will work as well. It will just use a reasonable default configuration. If we want to include it, it goes at the root of the repository. And then we go to this address on the GitHub marketplace, where we will find the codecov GitHub application. We just have to click on it to install it on our GitHub account. And once we have done this, in the pull request pages, we will get these reports that you are probably familiar with. So the codecov reports appear in the checks at the bottom of the pull request, and the codecov will also post a comment in the pull request discussion with a short summary of the coverage reports. And at this point, we already have a continuous integration setup that we can use to test our application and be more confident in the fact that we are always preserving the quality of the master branch. And this, having this insurance and this test suite that keeps running constantly means that our code will have a better quality because we are less likely to introduce bugs. And also we can be more dynamic and ambitious because we have this kind of safety net that will help us make sure that we are not introducing patches that will break existing code. On different platforms such as Travis or CircleCI or AppVeyor, the process is very similar, and they are also straightforward to use and very clearly documented. And you can see this tiny repository for minimal examples of configuration for Travis, CircleCI, and also Tox. And of course, I really recommend for real-world examples, having a look at the configuration of projects that you know and use, so NumPy, SciPy, Nilearn, and scikit-learn, and read their continuous integration configuration files to see what it looks like for realistic size projects. And again, for local testing, at least, it's a good thing to use Tox to generate virtual environments and test in many different virtual environments. And it can be combined with the continuous integration. So we can also run Tox on the continuous integration machines. That's not a problem. I saw your question, Elizabeth. I'll answer just a bit later. I see that someone asked why Nilearn use a mix of different CI platforms. So I'll answer that now. Indeed, Nilearn uses Travis, CircleCI, and Azure pipelines. All that Nilearn does, you could do on either of these tools. Although maybe storing artifacts is a bit more tricky with Travis, but I'm not sure. But for the other two, for sure, you could run everything on one platform. But for historical reasons, we have been using several of them. And also, before we were using AppVeyor, we stopped using it now. But I think one important reason is that we are using the free versions of these services. So by spreading out the different tasks that we want to run on different services, we can get more virtual machines for free. And when you open a pull request, you will, Gail said that, Travis will not store the artifact itself. So on Travis, you would have to upload the artifacts to Amazon. And when you open your pull request, you will see all of these checks on these different platforms. And here are the relevant configuration files. So to figure out what is going on, you can have a look at these files and at the scripts that they run. One small detail that I want to point out is that CircleCI runs builds the documentation. So it executes all the examples and runs things to create the HTML documentation. But as this can take a long time, it is cached, so it might reuse the build documentation from a previous run. If for some reason that's a problem and you need to invalidate this cache, just write anything you want in this file here in the .yaclci hidden subdirectory, and it will invalidate the cache. Now, to conclude, a few tips on how to make efficient use of this continuous integration infrastructure. As it takes quite a long time to run, you don't want to run everything to discover at the end that there was a syntax error in your code. So at least some checks you can run locally before pushing to your pull request branch and running the whole test suite. So at least I would recommend testing the tests that you have added or any tests that involve the code that you have touched directly, possibly running the complete unit tests. If you are adding new examples, run the examples you are adding or those that you have changed. And something that's really useful is makedoc, not make.plot, which will build the HTML pages of the documentation without the plots, so without running all the examples. So like this, you build the documentation very quickly. It's missing all the plots, but this way, you don't have to run the many examples to discover that there is some syntax or indentation problem in a doc string. Then once you push, as I explained, a bunch of things will happen on different platforms. And if it fails, most of the time, it's a genuine failure, which means that there is actually a mistake in the code we are trying to introduce. But that's not always the case, so it can fail for other reasons. For example, a package that we depend on has just made a release with breaking changes, so the master branch is broken as well. Or the most frequent case, the examples need to download dataset from online servers, and if one of these servers is down, running the examples can fail, or even some tests. So if what can be useful is to check if other pull requests or if master are also failing, to tell if it's a problem with the changes you introduce or if there is a larger problem. But in any case, the answer is in the continuous integration logs. Of course, they are quite verbose, so they can be a bit long. They're it's really not convenient to read them in the web interface, but there is a button at the top to download them. And then I recommend just downloading it and searching for fail in all caps. Most of the time, the interesting information will be close to that word. And of course, if the tests are running are passing on your machine and you don't understand why they are failing on the continuous integration infrastructure, don't hesitate to ask for help. And that's everything I wanted to present today. So thank you very much for your attention. Now I will answer Elizabeth's question. So containerization, yeah, as Kshitish pointed out. So the question is, could you talk at all about how continuous integration compares to or interacts with containerization? So as Kshitish points out, of course, containers are very heavily used by the continuous integration platforms themselves. Very often, they can clone and check out our code directly on the virtual machine. But very often we are using a Docker image. So on the continuous integration platforms, our tests run inside a Docker image. But I think your question maybe was that if we develop code inside a container image, we can share that image with someone else, and the code will run just fine in the container on their machine. But when we are developing a library, that's not at all what we want. We want our code to be really robust and portable, and work on any user's machine, or as much as possible. So we are not forcing the user to use virtualization to mimic our environment on their machine, but instead we improve the quality of our code, and we test it on many environments to make sure that it will run on the user's environment, and they don't need to adapt their machine to be able to run our code. And in the case of a library, the containers will not solve this problem at all, because if the user is creating a new project where it needs to, it will have several dependencies. One of them will be Nilearn, but there are others as well. If each dependency that he wants or she wants to use is telling it that it should run in this exact environment, there will be conflict, and basically the library is not usable and will not be adopted by anybody. So Docker containers are really awesome and very useful, but this they don't make it optional to ensure the portability of library code. They could be used, for example, at the end of a continuous integration pipeline. The continuous integration job could build a Docker image containing our freshly checked in code that can then be, for example, deployed to a production server if our code is a web application. So yeah, as Gael is saying, basically if it works just on a particular Docker container, it's basically the same thing as working just on a machine, except that it's easy to share the machine in question with other people. These CI techniques are definitely available to self-hosted GitLab repos. I'm not sure what you mean by self-hosted GitHub. But yeah, if your code is on a private GitLab or on Bitbucket or on GitHub, you can use these continuous integration techniques. If you don't want to give access to your code to any of these outside platforms for reasons of sensitivity, you can implement the same principles, but it will be probably a bit more work. But Git, just like any other version control system, has hooks, so you can use these to trigger some build on your on whatever infrastructure you are using to host your remote repository. And I don't see any other questions. So,
yeah. I think it's good. We're also right on time. Thank you very much, Jérome, for this very informative and comprehensive talk. That's very great. I think if people have questions directed to you, they can either write them here in the chat, or we can address them during the code sprint or later on. So I'm gonna remove you from the video, and then I will get our next speaker on board. Just a minute. Okay, here we go. Let's see.
Hey.
And there we are. Hey, Alejandro, how's it going? Good, good.
Can you hear me all right?
Yeah, you're all set up and ready to go?
I'm ready to go. Let me just share my screen.
Yes. Okay, while Alejandro's setting up, I'm gonna write an introduction. Maybe that gives you time.
Freezing. Hold on. It's sort of frozen. Hold on.
Yeah.
Uh-oh.
I mean, otherwise, just reload.
Give me 1 second.
Yes.
It seems like something froze something. Oh no. Can you see my screen or is not?
We can see you, and Gael is asking if you're using Chrome because that supposedly works better than Firefox.
Oh, that's probably the problem. I'm using Firefox.
Okay.
Might have to give me 1 minute then.
Yeah,
because
sure.
my whole computer froze actually, which is weird.
Okay,
so
I'm gonna, yes, I'm gonna close the video here. Okay. Then while Alejandro is restarting and setting up, we just gonna wait for him. Gael is asking a very important question if he had to try to turn it off and on again, which is of course what we always do. But yeah, he's about to do it, so gives us a few seconds to breathe and relax. I'm just gonna have a sip of water here. I mean, it's all part of this process we're all trying to figuring out right now in these weird times, right? That being said, I think it's working, or it did work reasonably well the whole day. So also, in case you know someone that still didn't get the update that we are not switching rooms or sessions for this, we are going to stay here also for our Alejandro's talk. So if you know someone that got lost, maybe just re-invite them. So I'm going to check if Alejandro is back. There he is. See him, but not live. Okay, just going to take a while. Okay, maybe while we wait, this might open up the possibility to bring someone else on screen in case of questions or comments, short ones though, right? Because as soon as Alejandro's back, we're going to continue for the sake of time. Okay, there he is back again. So trying it again.
Hey.
Hey.
Hold on. 1 second.
Oh, yeah.
1 second, 1 second, 1 second.
Yep.
Can you hear me okay?
Yeah, I can hear you.
I can't hear
fine.
you, but that's okay because I'm presenting. So let me just try to share my slides and I'll just go ahead. I'm still on Firefox, so hopefully that works. But Chrome is not really going to work for me. So there we go. That looks a lot better. Okay. So if everybody can hear me okay, I think I'll just go ahead and get started. I don't think I need to listen to anybody since it's just me talking to myself. Sound good? Okay, perfect. All right, so I'm really, I think I'm gonna give a less technical talk than what you've heard today. At least what you heard the last two talks were brilliant. And I'm gonna end on a little bit of a lighter note. So I was asked to give like a, I was asked to give a sort of overview of the Python ecosystem for neuroimaging, and which I'm really happy to report is just in a fantastic condition, honestly. I think we've come a long way from where we were. I've been involved with the neuroscience community, you know, I don't know, 10 years now. I started out doing stuff in FSL with Bash and fighting with my advisor, trying to get permission to use R and then permission to use Python. And, you know, to be honest with you, it was a little bit harder to justify at some point in time because the tools were not there yet. And there was times that it took a lot more effort for me to do what I wanted. And now I think it's a lot easier to justify because I think you're going to be doing better science. So hopefully I just give a slight overview of other projects that are going on, how they interact with Nilearn. And really I want to give more of like a high level overview of what are good principles. So I'll go to my overview slide. What are good virtues of a modular ecosystem? So what does it mean to have an ecosystem in the first place? So I'll give you a really quick tour. And then I'm going to use NearScout as a case study, of course, because it's my project. And hopefully, it's not really supposed to be about NearScout. It's hopefully just shows you how there's different pieces that come together to make NearScout possible. And it's really thanks to those projects that NearScout even exists. And what are some lessons that we can gain to maintain this healthy ecosystem and to make it even stronger? So, first of all, I think that we want tools that will match our scientific aspirations. So we honestly have extremely lofty scientific goals. We want to image and visualize the human brain, the structure and the function, and we want to relate it to cognition, behaviors, and traits. We want to understand how the brain gives rise to complex mental states, create biomarkers of brain disease. I mean, these are things that could change the world if we do them right. But unfortunately, there's obviously been a lot of crisis about whether or not we're doing that. And I think one of the key factors to doing science that really matters and changes things is trust and transparency. So do we even trust our results? Can we understand, related to software, can we understand the code that produced these results, these images? And can we fix bugs if any arise? Or is it going to be pretty much completely impossible? And can we share these results and these pipelines and the data, and can our colleagues reproduce and modify our pipelines and reproduce our results? So these are key scientific principles that I think we want our software to help us with. In neuroimaging, there's a really wide range of analyses, and I think they're fairly specialized. So there's like image pre-processing, there's the manipulation of images. We have all sorts of structural analysis, different types of functional analysis, decoding, mass univariate GLM, functional connectivity. We need visualization tools and maybe even meta-analysis tools. So does this ecosystem support this wide range of scientific questions? And so, I mean, one place to start is, what is wrong with monolithic packages? So, SPM, AFNI, FSL, they're really robust and mature neuroimaging workflows and software. And honestly, I think that to some extent, these can be very appealing to beginners because they're potentially easier to use and understand. So why don't we use these monolithic packages? Why are we trying to, support a different system? And I think even though I have to say FSL is not actually purely, fully monolithic, it's actually, modular, thankfully. In practice, most users are going to use these packages in a monolithic way. They're not going to often naturally mix them with other pipelines. And I think really more importantly, because the code base is often in a language, at minimum, a language that you may not be scripting with. So it's written in a language that you're not actually putting together your scripts in. And just of the way that the code is organized, it's more opaque. And so this requires more expertise to debug. So if there was ever an issue that came up that was actually affecting your results, I think that might be really hard for an end user to do. So this kind of encourages a really large gap between an end user and a sort of software maintainer, software developer. And I think that's generally a bad thing. It's amazing that we've actually been able to get this far doing that because it does require an extreme amount of time from the software maintainers. But I think we want software that will encourage introspection and hopefully have a more diverse and sort of distributed maintenance, regime, if you will. So what we really want, I think, is modular design. So like I said, I think specialized analysis pipelines sort of naturally tend to monolithic structure. Modular design is really hard to do properly, but it has some major advantages. So first of all, I think code is easier to test. So when you have a piece that has a small defined function, it's easier to say what it should do. So when you have a library that is only doing I/O, it's easier to say these are the results I should get from this I/O library. So you can increase the testing, have greater coverage, and in turn increase trust, which again is scientifically important. Then this also makes your code more reusable, right? Because it's not just something that I'm going to use in my package. So if FSL, for example, well, I don't know if FSL is a best example because it's actually somewhat modular, but if a package has a tool that's really useful, but it's deeply embedded into their monolithic framework, it's going to be hard to reuse in another context. Somebody else is going to write something that maybe is a port of it that is exactly the same. So now you have two codes in two different languages with greater maintenance cost. And I think if you do things in a certain way, it can also promote extensibility. So you don't just want your code to be used in the way that it was intended to, but hopefully it can be expanded and built upon to build more complex pipelines. So what are some principles of a healthy ecosystem? I think we want modular, well-defined, reliable building blocks. So we want to build upon these really core blocks. These blocks should have clear, consistent APIs. They should be easy to understand. They should be predictable. They should hopefully behave similarly in different scenarios. They should be accessible. The code hopefully is somewhat easy to understand, and that's a Pythonic principle. Obviously, great documentation we've heard about that really helps with onboarding for new projects. I think ease of contribution is really important. So if there's developer guides, if there's active, receptive community that can help, and really in relating to modular design, interoperability. So modular design and standard formats really are what's going to make it easier for tools to interact and actually be an ecosystem instead of a bunch of silos. So with that said, let's take a quick look at the neuroscience, neuroimaging ecosystem. So first of all, this is really all possible because SciPy, and I think Python in general, has a very modular ecosystem type of approach. So there are specialized libraries that are extremely good at doing one thing. So NumPy is just, we can all use NumPy. We can all accept NumPy objects, and we can all trust NumPy to do its job. So I don't necessarily have to worry about how to map data to memory. Somebody else has done that. They've done it really, really well, and I can take that piece and I can trust it. So we have this amazing set of tools from Python that we can build on. And then we have a set of tools that I think help us with some of the basics, like, for example, NiBabble critically helps us with reading neuroimaging file formats. We have tools we have data standards like BIDS and tools like PyBids to help us deal with those data standards, or tools like Hudicom to convert to those data standards. And then we have tools that can help us also get data. So obviously, without data, can't do much. And then the ecosystem has really grown to have very mature packages for data analysis. And so PyMVPA, Nilearn, I put Nilearn stats separately because that's a new addition to Nilearn. And DiPy, MNE, these are all very mature, and I think for the most part, designed in a modular way. So there's a lot of pieces of these different libraries that as a developer, I can pick and choose and use different pieces without necessarily having to buy into everything about that package. So I think that's a really good design principle. NiPipe is, I think, a really interesting example because if you're not familiar with NiPipe, I'll talk about it a little bit more, but NiPipe is essentially it's a workflow engine for neuroimaging workflows. So one of the main things that allows you to do is use existing tools that are not necessarily in Python and use them in a Pythonic way, essentially, have a clear, consistent API. And then, of course, we have also tools for plotting, which are really important in neuroimaging because we're trying to visualize the brain. And so on top of these sort of core packages, then we have a huge variety of sort of applications, if you will. So this is just a small subset. So, I mean, I'm sure there's a lot of people watching. They're like, hey, where's my package? There's too many, but this is just a random selection I could find. And as you can see, this is actually almost overwhelming at this point. But I think it's a really good sign that we have a really mature ecosystem. So obviously I can't talk about all these packages. So I'm just going to use NeuroScout as an example, and I'm going to touch on some of the tools that NeuroScout relies on and how they work together. So what is NeuroScout? This is the project that I've been working on. NeuroScout is a web-based platform for fast and flexible reanalysis of naturalistic fMRI. So we have taken a bunch of open movie fMRI data sets and used machine learning to annotate them. So we have potentially hundreds of possible regressors on a dozen open naturalistic data sets that look at different movies like Raiders, Forrest Gump, etc. So a really diverse set of data and a huge set of regressors automatically generated. And then we've created a web platform, which you can go to if you want, nearscout.org. And users can create custom statistical models using a web-based platform. So the idea is really to have automated data retrieval, modeling, and sharing. So you can go from the web-based platform to create a model. It creates a package that's a self-contained bundle with everything you need to run that. And in one line, you can run that bundle, get fitted results, and upload them to NeurVault. So, this is only possible because of this ecosystem that exists. So almost everything that NearScout is, not entirely everything, but almost everything that NearScout does is just to glue these different pieces together. And so actually, as a maintainer of NearScout, most of my time, maybe not most of my time, but a large percentage of my time is spent maintaining the upstream packages that we rely on. So first things first, is not really exclusive to Python, of course, but I think this is a great example of one way to increase interoperability is data standards, or just standards in general. So if you're not familiar with BITS, which I'm sure most of you are, it is a standardized file folder structure for neuroimaging datasets. Using a combination of nifty headers and JSON sidecars, we can keep track of the metadata of different files, and using a structured file format, we can also keep track of different attributes such as the subject ID, task, etc. And so what's great about this is this allows for generalized automated analysis as all the information is programmatically accessible. So this is awesome, and this makes my job, not just easier, it makes it actually possible. So that's just the foundation. I think that's one way to allow interoperability between the different parts of the ecosystem. So now that we have a data format, we need to retrieve our data. So I could talk about DataLad all day long, but I'm not going to, because there's a great handbook. So DataLad is a Python data management tool based on Git. So in short, it helps you keep track of your code, data, and metadata in Git repos, that's supposed to say. It's a tool for discovering, consuming, and publishing large remote data sets. So essentially what we've done is we've taken data sets and we published these pre-processed data sets. And so this is actually just a short snippet from what NearScout is doing to get the data. It's simply just saying, install this data set and get, for example, here, I can, in a granular way, say, just get all the files related to subject 1. That way I don't have to download the whole data set. If I'm only running a model that, oh, it's hiding behind my head. Okay, well, that's not good. It's going to hide a bunch of stuff behind my head. But essentially, the idea is you can, in a granular way, control the data that you're getting. So I think this is really cool. I definitely encourage you to check it out. And here's an alternative. So Nilearn has a datasets module, which I'm sure you're familiar with, but I think this is another great example. I think we need this sort of stuff. We need built-in dataset fetching. This is really important for reproducibility. This is really important for examples, documentation. So here's a short code snippet of how you could do something similar using Nilearn. So, one thing that's a running theme, I think, in this talk I want to make is ecosystem doesn't necessarily mean that everything has to be done the same way. So there can be parallel solutions. That's okay. There's going to be times that we're going to want to merge approaches, but I think it's not necessarily true all the time. So we have a way to get the data. Now we need pre-processed data. So this is where fMRI prep comes in. So fMRI prep is a robust, reproducible pipeline for minimal pre-processing of fMRI data, and it's built using NiPipe. So like I said, NiPipe is a platform for providing a uniform Python API to heterogeneous existing neuroimaging software. So that's really the key, I think, contribution of NiPipe. It's a way to essentially access different interfaces that are not written in Python, but we know provide very useful neuroimaging tools and provide a way to access them from within Python in a way that makes it easier to mix different elements of them and create a more complex workflow. And I think this is actually a really interesting example because in some ways, I just told you we're trying to get away from using these other tools, but it goes to show that really the only thing that these tools are lacking, because they're fantastic tools with great algorithms, it's really just this uniformity and this way to make them interoperable. So NiPipe solves that problem. Although I will say one con of NiPipe, if you're using it in the intended way, is that if you're using an FSL interface or an SPM interface, there's still a greater distance between you, a Python developer, and the code. So you might still run into the same problem that, if a bug is going on FSL and using NiPipe to access FSL, you might have a nice uniform API for it, but you're still going to have the problem that it's going to be hard to contribute upstream to FSL. So it's something to keep in mind. So this produces a nice data set. It's actually something that then we use Data Lab to create this remote repo that we then download. And so once I've done that, really, I'm actually it's not even NeurScout anymore. So now it's actually Fitlins. So this is, you've heard from Chris earlier today, and Chris is the main maintainer of Fitlins. Fitlins is a bids-aware GLM estimation framework. So Fitlins takes a bids data set, which you know what that is, and it takes a bids derivative too, because it takes a fMRI prep data set, which is actually a derivative data set, and it takes a bid statistical model. So I'm not going to talk in detail about what this is, but it's just a JSON representation of a design matrix, and to construct a design matrix and construct contrast. So this is an example of a way to, again, increase interoperability, is to create these standards that different tools can read and different tools can operate on. So this is what actually makes it possible to give Fitlins reproducible instructions to create results using a data set. So great, we have all these bids things though. So how do we actually deal with them? And so one tool that we've been working on a lot, and the primary developer is Tal Yarkoni at this point. He's created a lot of, well, actually, he's just the main developer. PyBids is a tool for querying and extracting metadata from bids datasets. So this is a great tool if you're dealing with bids datasets to access them in a way that is programmatic. And essentially what it allows you to do is it allows you to make complex queries using those structured file attributes in a Pythonic way. So for example, in this example, I built a bids layout, which is essentially just a representation of that data set. And it tells me your data set has 54 subjects and it has 1 run. And then I can tell that layout, hey, I want the bold file for subject 1, and I want you to give me back the file name. Okay, so I can do that. Once I get that, and actually I think there's a slight error here, but once I get that object back, because I can also get it back as an object, then I can ask, give me some of the metadata related to this file. So for example, what's the task associated with this file? What's the, oops, this typo is supposed to say repetition time. What's the repetition time associated with that volume? So this makes it really, really easy to parse and consume bids data sets using a pure Python API. So highly recommended if you're using bids data sets. And another aspect that's newer, and a little bit more alpha, if you will, is the bids model specification. So what we're doing here is using PyBids to take that specification and take that data set and essentially create a design matrix for us. So this makes it really easy to get a design matrix that's ready to run. But before we run anything, we need to read the data, and I mean really read the data. And so I think sometimes something we take for granted are these really foundational pieces. And NiBabble is one of those foundational pieces. So without NiBabble, we really wouldn't be able to do any of this, because we'd have to go and look at nifty headers, and we'd have to read all these images and know all the different intricacies of how these work. So this is a really, really great example of a tool that makes the ecosystem possible, because we all use NiBabble. We all expect nifty image, NiImage-like objects, so we can operate with those different types of objects. And so we don't have to worry about it. I will talk a little bit more about this later, but I don't have to care about how this is represented on the disk. I don't have to care about how this is represented on the memory. I can simply just use that object. And so this is great that we've sort of come to this standard, not just a library, but also object type. And then Nilearn stats. So this is a new module in Nilearn that was previously NiStats, that was previously NiPy. But it is a pure Python module for voxel-wise fMRI GLM. It has a consistent, easy-to-use Pythonic API, and it has support for all sorts of stuff that you might need to do such analysis, including hemodynamic models, design matrix creation, the statistical modeling, and of course reporting. And so this is honestly pretty much the code that Fitlins uses to actually do the model fitting. So as you can see, what I'm doing here, I'm basically just importing the first level model object. I'm importing the design matrix module and the plot design matrix module. And Nilearn is taking that PyBids design matrix, and it's creating a design matrix. I think it's actually ending up in pretty much the same format, but it's adding a drift model. It's adding a couple things that you might want in your model that may not be there. And I think it's creating a dense representation of it. So now I can just take that and plot it. So that plot on the left was made in that next line, and then simply create a first level model object. And using a familiar fit transform API, I can give it the design matrix, give it the image, and get results. So yes, I noticed the docs were not merged yet, but the nice stats still has some nice docs that you can go look at. But this is honestly, if you know how to use Nilearn, you're going to know how to use this extremely easy, and it gets us away from FSL finally. So I mean, I actually think FSL is great in many ways, but what this is great is that when a bug comes up, which has happened, I've contributed to nice stats, and it was great because it was really easy for me to go in there, find the bug, fix it, and contribute a PR. So highly recommend it, and I think it's a great example. One thing I want to highlight here is that the way Nilearn stats is designed, it was not designed with, I know there's really not that much hate for FSL, but the way Nilearn stats was designed made it really easy for me to do this. And they didn't necessarily think of, any of what I'm doing as a use case, but because it's designed in a way that's modular, in a way that's, independent, it's really easy to use in a flexible workflow. So yeah, this is sort of what I said already. And so this is a great example. If you want to use it in a way that is more high level, there are some functions that make it easier. So for example, there's this function first level model from bids that will take a bids data set. You give it a task label, a space level, point it to a derivatives folder, and it will create your models. It'll give you the run images, the events, and the confounds. So you can fit this right into the first level model function and fit your model. So different approaches. This doesn't use PyBids, but I think it's great because the way that, again, Nilearn stats was designed, it did not assume that I was going to use this higher level function. So it gave me the option to use a lower level function that's more general while still providing a higher level helper function. So I think that's a great approach that I think Nilearn embodies, and it makes for a really healthy ecosystem. So finally, pipelining. We in Fitlins use NiPipe, which arguably is overkill, but probably just because we're familiar with it. It works for us. It provides deployment via execution plugins. It provides disk caching in between nodes. But another thing you could do, which many of you are probably familiar with, is joblib. So joblib is used internally in Nilearn, but it's just a lightweight pipelining tool for Python. It provides transparent and fast disk caching, easy native parallelization, and is optimized for NumPy arrays. So again, an example of how in our community we have different approaches to the same solution. And if you, for example, were going to be dealing with other tools that are not in Python, you might want to use NiPipe if you're familiar with it. I'm sure Chris can tell you more advantages. But if you wanted a lightweight approach, you could also use joblib. So we have those trade-offs there. So now that we've run our analysis, we want to share it. And so another way to do this is to have a standard output. And so I've already mentioned this a couple of times, but this bids derivatives is a standardized output for neuroimaging pipelines, and it captures the data and the metadata necessary for a researcher to understand and reuse these outputs in subsequent processing. So again, it's machine readable. And another thing I'd like to point out is that PyBids facilitates writing out these paths. So it's actually really easy to create a bids derivative data set using PyBids because you don't have to construct that path manually. You can just say, these are the attributes associated with this path that I'm about to create. Give me the file name. So I encourage you to read on this project if you're not familiar with it, because I think it's going to become something that we're going to see everywhere. And finally, visualization. So Fitlins generates comprehensive HTML reports of results. And again, that was really trivial to do because we have Nilearn. So I was able to just take this plotting module from Nilearn and give it a standard, nifty-like, NiImage-like object, and it's able to plot it. So again, a great example of a tool that was internally used in Nilearn for everything, but is designed to not just be used internally. It can be used by other tools. So that was really the tour of the tools that NeuroScout relies on. And so I like to just close by, saying this sort of interoperability is really powerful. So by having tools that talk to each other and are designed in a modular way, it facilitates the creation of these high-level complex applications. You don't have to worry about how the layer works, And I think two main ways that we can do this are converging on standard data models. So for example, like I said, NiImage-like objects, nifty file formats. We can also converge on models for the BIDS dataset, the BIDS stats model, the BIDS derivative. So these are, standards that we're all accepting and, allowing as input and output. But I think another important part, it's not just standards, it's also this modular design. So like I pointed out several times, a useful library will not necessarily make super strong assumptions as to how you're going to use your modules. So it's going to be made as independent as possible from other modules in the library. So I can use the Nilearn product library, or I can use Nilearn stats. And I'm not necessarily an expert in other aspects of Nilearn, but it was really, really easy to just take that aspect of Nilearn and use it in my application. But modularity is really hard. I think there's actually a constant tension between, getting results now, getting those fast results that your PI wants, and, writing maintainable general purpose code. So I think, Gal talked on this earlier, but I think having that long-term vision really helps, realizing that this is not just because we like to design software. This is going to make better science. I think it's important to keep the basics simple in general. So, build small units that take general inputs, and then build high-level integration layers. So make your tool usable at different levels of abstraction. Don't just assume that everybody's going to come in and going to want to use your package in a monolithic way. Iterate and prototype. So, avoid premature over-engineering. That's easier said than done. Might take you a couple of years to learn that one. At least I'm still learning it. But I think it's something to keep in mind. And, be careful with releases. So if your software, if your package, if your library is maintained at a certain level of standard between releases, it makes it a lot easier to use in a more complex pipeline because I know what I'm going to get. And, one of the problems with modularity is keeping track of all the dependencies can be really difficult. And I think, there's also some social challenges. I don't know if this is a social challenge, but, hidden bugs can lurk in low-level packages. And, working with these base building block packages, it's not as fun. It's not as exciting. For example, in NiBabel, luckily we have some really dedicated maintainers like Chris, but it's not something that people necessarily want to touch. And I think people should try to, as much as they can, get involved in these packages. These are really important. And without them, we wouldn't be where we are today. So don't be afraid to look into the code for them. Don't be afraid to ask, is there a bug? I think sometimes it can also be friction between packages. So it's not necessarily always easy to adopt a standard. So I think that's just natural. I don't know if there's necessarily a solution, but it's just something to keep in mind. Harmonizing efforts can also be difficult. A lot of times someone creates a library, somebody else creates a library, does the same thing. And there's limited resources. Sometimes I ask myself, should these projects be joined? I think there's a lot of times that they should be, but I think that's just how science is. So people are going to want to try different things. I think that's perfectly okay. But I do think that this makes it hard for onboarding. So I think it's something to also keep in mind as developers, as people that are experts and familiar with all this ecosystem. I think, as beginners, I remember when I was first joining the community, it was just really overwhelming because, I would hear, oh, use DataLad, oh, use this, oh, use that. And so half of those packages, well, maybe not half of those packages, but a good amount of those packages that people told me to check out, they were just their pet project of the week. So I think this is something we need to be actively helping beginners with. So I think having courses such as this, I mean, there's so many courses now that really help with this, but, to give an overview of this ecosystem and to help onboard users so they can kind of pick out, these are packages that are actively maintained. These are packages that everybody's using. I think that's really going to help. But again, it's also okay, to build, I think, applications that are high level. Like NeuroScout is very high level. And I think, not all users will be developers, and that's also okay. We have to accept that. And I think one way to get people to come on board is to build these high level tools, and then maybe hopefully some of them will trickle down and use some of the more low level tools. And let's not forget, NiPipe's a community. So again, let's contribute across the stack. Let's, keep making pull requests. Let's try to be, friendly and, responsive as much as we can in our projects. And just remember, we can talk to each other and figure these things out. And these better tools really are going to make better science. So hopefully the funding agencies continue to notice. So yeah, thanks to everybody. That's it. And yeah, if you have any questions, I'm looking at the chat. So happy to take any questions.
Okay, Alejandro, can you hear me again? Apparently he cannot.
Oh, and I can't hear you, but
okay, there we go.
I can see the text. Oh, there we go. I can hear now. I can hear.
Oh, okay, great. So first of all, thank you a lot for this amazing introduction overview into the Python ecosystem for neuroimaging. And before we forget, just that we have everything on board here, as I couldn't introduce you at the beginning, better late than never. Alejandro is currently working as a research scientist at the University of Texas, Austin. And you already got to know NeuroScout, so that's good. We actually have one question for you. Okay. And it's in the Ask a Question tab down there.
Oh, I see it. I see it now. I see older questions. So which one are you?
The third from the top. Otherwise, I can just...
The one about the... Yeah, just read it to me. I don't know which one you're talking about. Okay. Yeah. Resources on how to organize project paper-specific repositories. Actually, I don't know if anyone else has a suggestion. I think Chris made a comment there. Yeah, I think NiFlows that Chris mentioned is a good one. But I think actually this might be something. I think it's something that we could work on, but I think it's also hard because I think projects can vary so much. It's hard to make, template that necessarily works for it. I'll see if I can think of something, but I think there's, like Elizabeth's saying, I think there's a lot of template makers that are not necessarily neuroscience specific. And a lot of times the way we organize our packages, I think just reflect how packages should be made in general, like Python packages. So I think there's some good suggestions there, but I don't know if it necessarily has to be neuroscience specific, except for maybe like papers. I think that might be something that it would be very useful to have.
Great, thanks a lot. We actually have two more questions if you go to the bottom of the question tab. See that one is distinction between...
conspicuously missing tool.
Oh, yeah.
I don't know. You tell me. Probably.
And the one above that, I think, is also for you.
I think it is. The question is the distinction between modular and monolithic. I think it is fuzzy. I think it's fuzzy because a lot of the packages, like I was saying, FSL, and I only know I'm going to talk about FSL because I'm more familiar with it. But FSL is modular, so I think that's actually really great because we've been able to use it in NiPipe in a modular way. So we can take a lot of aspects from FSL and combine them with other aspects. But I think what you're saying is that as a relative outsider, it can seem monolithic. And so I think it's really a distinction in terms of, like I was saying in Nilearn, a lot of these little pieces can be used separately. So I think it's a fine distinction sometimes, but I wish I had a better example, but some of the code I wrote before, for example, I would write code for plotting, and it would require an object that was my object, that was only I knew about in that library. So that plotting code would not work with just a general format. So I think these are the sort of things I'm talking about. And I think Nilearn in particular, I can imagine why it seems monolithic, because it has such a wide range of functionality. And so you can do, functional connectivity, you can do GLMs now, you can do machine learning. So I can see why, I can see why it feels that way. But I think when you actually try to combine these tools, the lower level modules, I think, are designed to be not monolithic, to be modular. So yeah, I think a lot of it just comes from, like I said, it's hard to get your head wrapped around how all the parts of the ecosystem talk. And I mean, to be honest with you, it took me like years to figure that out. So I think it's something we could work on. And I think education is what we need to do.
Thanks a lot for addressing all the questions. I think that's it actually for the questions, and that's your presentation. Thank you so much again. It was amazing. Great to have you here.
Thanks. Yeah. All right. You go ahead and kick me off.
Yes, we'll do that. I'm just going to bring back Gael here. Okay. So everyone, please stay or remain seated. I'm sorry. Gael will be joining us again on screen to provide some concluding remarks and an overview of the next couple of days. And there he is. Gael, I can't hear you. I don't know if the others can. Okay, I think he's saying he's trying it again. Yes, that appears to be correct assumption. Okay. Nope. Okay. Okay, now we're gonna just wait again. Apparently, this is my curse here. I'm sorry if that's related to my setup. And while we're waiting, I can finally address some questions I was getting before because I did not pay attention to the chat. I'm sorry. Gail was actually asking me what kind of music I was listening to, because that's a topic Gail and I talk about a lot. Mostly like post-rock, prog, a bit of math as usual. Whatever helps you get along with coding, which I find that kind of music is really nice for. Stoner rock works as well. And actually, another question I can think I can address here, Chris, at some point there was a discussion about PLS, I think, it seems like. And Chris M mentioned that NiBeta series also implements PLS. As far as I know, it's least squares all and least squares separated at the moment. But it might be something in the works. Okay, and we're gonna try Gael again. Gael? For me, still no sound, I'm sorry. Could the others provide any feedback if they hear sound? Nope, okay, no sound for anyone. Let me just briefly toggle your mic and toggle it back in. Maybe that makes a difference. Nope. Doesn't seem like. See, now speech to text would be great. Yeah, could you try the remove your headphones, maybe? No, no. Okay. Okay, folks, we keep trying here a bit. And if not, I will do the honors. Chris suggested I just lip read Gael. That's a tough nut to crack, man. I can't really. But okay, and to not stress our times any further, I would say I try to say whatever Gael was trying to say, which would not work out well, I think, but here we go. First of all, I would like the audience to joining me in thanking all the organizers and the presenters from today, because it was an amazing conference so far. Great talks, very informative, great overviews. It's a great job. It was a lot of work went into this, especially now that we have to do it virtually. It's great stuff. And I think it's especially important to stress once more how actively engaging the Nilearn community is in being interested in getting all these new contributors and developers in, right? Then, as you might be aware, for the next couple of days, tomorrow and on Thursday, we're gonna have the coding sprints, where there, if you go to the Nilearn GitHub repository and through the issues tab, you will see a nice list of issues that are or should be tagged respectively in terms of great projects to address during the coding sprint, great first issues if you're new to Nilearn. As you heard a bunch of times today, everyone that is currently in the Nilearn development team is very interested in extending the development team, thus very up for helping you if you should encounter any problems or have questions. And then on, I think tomorrow, there's gonna be the only real scheduled event, as far as I know right now, will be the discussion about the Surface support and implementation, which should be, it's at 10, I think. But you can also read it up on the schedule that we have online. Then on Friday, we will see each other again for the scientific day, where we have an amazing lineup of speakers presenting their work using analysis that are supported by Nilearn, but maybe have not been fully conducted in Nilearn. And yes, Elizabeth just sharing the information for the sprint. Thank you a lot. It's now posted in the bottom of the chat, so you might want to check that out. And if you don't have any further questions, comments, remarks, then I would say we will end the broadcast now and hopefully see all of you tomorrow for the coding sprint and or Friday for the next session of talks. Just gonna give it a few seconds if someone has something or just wants something to say. Okay, that doesn't seem to be the case. And that, thanks a lot again, and then see you these days. Have a good one, everyone, wherever you are.